meaning and context of those images. So to hear more, Professor Li.
Thank you. Thank you for the great introduction, and thanks for coming. It's actually nice to be here because outside is so hot. So indeed, I'm going to share with you some of the exciting research and just the field of computer vision in general. So let me ask you a question. How many of you think you know what the word artificial intelligence means? Raise your hand. Great. Okay. Don't worry if you don't. Here's a crash course for you. If my computer works. So I hope you've seen the movie Wally. And I just took excerpts from Wally and show you that if you were a scientist designing Wally, you're likely to be an artificial intelligence researcher. And you'll be empowering Wally with all kinds of functionalities, such as tracking, navigation. Where's the mic? I think. Test. Test. So I was saying that if you're an artificial intelligence scientist designing Wally, you're likely to be working on making a computer that's sitting in the brain of Wally to do all kinds of things like what I'm showing you. I took excerpts from this movie and just kind of labeled the functionalities that we want Wally to do, or his robot friends, like this one. So the list can go on and on. Here I'm just showing you all kinds of cool things an artificial intelligence system can do in the context of Wally. Let me move on. So artificial intelligence is this big field that is making exciting futuristic research, and one day hopefully will be helping all of us, and it's already making huge impact in our society. We have sent robots to the Mars, deep into the ocean, into the surgery rooms, hopefully soon into household, doing all the chores you don't like to do or your parents are asking you to do. And within the field of artificial intelligence, I'm most excited in the sub-area called computer vision. So computer vision is all about making computers to see. Here I just showed you a few examples. When you watch Lord of the Rings, you probably have not realized there is a tremendous computer vision technology behind it, especially for the character Gollum. I bet many of you have Kinect at home. How many of you have Kinect as birthday or Christmas gift? Oh, no, not enough. I thought everybody would raise their hand. Ask your mom or your dad to get one for you. If you can explain to them what the computer vision technology is behind it. Your digital camera has a face capturing system. That's what computer vision algorithms have done. We will soon, hopefully, be driving cars that have automatic visual system to detect roadblocks, pedestrians, and so on. So that's what computer vision is about. And here at the Vision Lab, which I'm the director of at Stanford, what we do is to build computers that see. That's our passion. That's our goal. We're not there yet, but that's what we want to do. So what does it mean to be seeing? There is actually a lot of meaning into that word. Let me just give you one take on this, one aspect of this. So a picture is worth 1,000 words. Some of you might have heard of this. What does it mean that a picture is worth 1,000 words? And what does it mean to computer vision scientists? Let's do a thought experiment, okay? So in this square box, there's supposed to be a picture, but I'm not showing you the picture yet. Instead, I will use 1,000 words to describe it. But the 1,000 word is a little long, too long, so I'll use 20 words to demonstrate. So I can tell you, it's kind of a dark background picture. It has bright purple spot towards the upper left corner. And then somewhere in the middle, there's elliptical shape and metallic kind of structure. And then down here in the lower right, you see round and big things. On the left, you see white blob and more blobs and texture. So I can go on, and you're sitting here like, oh my God, this is boring. It's actually not boring. A lot of this, you know, in order to even suppose you build a computer to write a description of this, it's quite an achievement. But that's not quite the way you and I communicate, right? If you want to describe to me a picture or visual scene that you see, you call me, you say, oh my God, I'm on a beach, it's gorgeous, let me describe to you what it is. You wouldn't be saying things like this. So instead, you're more likely to say, this is galaxy. Well, suppose you're sent to the space. There's a spaceship somewhere, and Wally and Eva are flying. And we see there's a part of earth and water. So this kind of description at the level of objects, sceneries, and movements, actions, makes a lot of sense to you. If I keep describing it, even though it's not as good as seeing the picture yet, you'll have a very good understanding of what the visual scene is. And in fact, this is the picture. So this is what we're passionate about doing. We want to give computers pictures and videos and have them understand it at the level that humans do, such that the computers can interpret it at the level that you and I normally interpret it and can communicate it and do meaningful things with it. So in our language, in research world, we call this high-level vision. It's so high, we're elevated to the space. So, so that's what we're passionate about. So let me also inspire you with something else. What is the best visual machine out there in the universe today? Your own human visual system. It's an incredible machine that nature has spent billions of years evolving. Just as the introduction went, half of your brain is involved or devoted to visual functionalities. It's by far the most incredible sensory system in your brain. And humans are incredible visual animals. Here's a very cool experiment I did when I was a PhD student. We want to show how amazing our brain is at seeing things. So here I'm showing you an actual experiment that if you were to come to my lab, we would conduct with you, is that we sit you in front of a computer and we flash photos at you. And then every time we flash a photo, we block it with some wallpaper-like thing. You might be wondering, what the heck is that? The wallpaper-like thing is actually to just disrupt your memory of that picture. It's disrupt the information. But in the meantime, we ask you, every time you see a picture, and there's a long pause, unlike here I'm just showing you in a fast speed. I ask you to write down what you see. And you're sitting in the audience, and you're probably already getting the picture that every time you see a photograph, you kind of know what the content of this photograph is, right? But it's incredible how fast I'm showing you these pictures. Here's an actual experimental result. We show this picture on the upper left corner for 500 milliseconds. How many of you, the children, do you know what 500 milliseconds means? Anthony, half a second. Excellent. Okay, so that's half a second. For 500 milliseconds, there is a Caltech undergraduate who wrote that whole thing for me. Oh, he didn't type with it 500 milliseconds. He only see this picture for 500 milliseconds, half a second. And then he's able to write novels. And he can write more if we paid him more. But it's amazing. He can write about the scenery, he can write about the objects, he can write about the activities that's going on. That's a typical human visual system result. It's this particular Caltech undergraduate is not special, at least not special for this task. I'm sure Stanford undergrad would write even more. And here's something incredible. In the experiment, we even shrink the presentation time of this picture to as low as, say, 40 milliseconds. Okay, now do you know what's 40 milliseconds? It's a lot shorter than 500 milliseconds. So it's 1/25th of a second. And within that time, your human visual system is able to capture important information like 2 people on a field. And it's just incredible. Every time I look at these, I conduct these results, I've been doing this for more than 15 years. I'm still so excited just thinking about what kind of incredible machine we have sitting in our brain. And our computers are pretty far from this, I have to say, and which again makes me excited. That means we have a great goal to achieve here. So that's pretty much what we are going after as computer vision scientists. We want to build computers one day that can just take an image like this and write stories for us, write novels for us. And that's a pretty grand goal, but we're making very good progress in achieving that goal. And the rest of the talk today is I'm just going to show you a few, just 2 or 3 projects that are going on, ongoing projects in my lab with my PhD student that's showing you the cutting edge technology in computer vision and how each one of these research is contributing to piecing the puzzle of making a computer that can ultimately see everything and understand everything. So the first project I'm showing you here is, we named it storytelling using images. And that's kind of trying to go for that holy grail goal of computer vision. And this is just an intermediate result. We have a lot to do, but we have made exciting progress. So what does it mean to write a story? In your English class, your teachers will be telling you the 5W rule when you write a story, right? The who, where, why, what, when. And one day, I want to make a computer that can write stories like this. It'll just write everything about what's going on in this scenery, who are involved, where we are, why is the tricky one, I guess. What's the whole event and when it is. So to make progress towards this, we first focused on 3 of the 5 W's. Those are slightly easier than the why and when. So it's the who, where, and what. So here is an actual result that computer in my lab we have built that can do. So that's an image, a picture we show to a computer. The computer have no other information other than seeing that picture. And then we ask the computer to kind of write a story, meaning to give us the who, the what, where, and who. And this is, on the right, is what the computer has done. The computer knows what is the event, it's a rowing event, where it's taking place. Computer tells you it's a lake, and who are the objects involved in this picture. And the computer would label there are trees, athletes, rowing boat, and water. So this is automatically generated by our computer vision algorithm. Here's another example. Here's another picture that We show the computer, that's it. We don't have any other information. Everything you see is everything the computer sees. And it's able to start label different objects. It labels snowboard. It labels the person. Look, watch, the computer is not only labeling, it's also, we call it segmenting. It's actually telling you which part of the image belongs to that particular object, which is not an easy task at all. It labels this as a human. It labels the cloud in the sky, the snow, and the tree. So this is, again, another result automatically generated by the computer in our lab. Here's more examples I'm not going to bore you with. So here's just quickly, this is a rowing event again, and the computer labels boat, or, if you don't know that word, it's that thing that you use to propel. Human, water. This is rock climbing. It labels human, rock, trees, and mountain, and sky. So of course you can see it's still a little patchy. So the computer has not achieved perfect result yet. But this is this is practically the world's first algorithm that does this level of understanding given a photograph. And by the way, all the photos I have shown you are just downloaded from Flickr. So these are actual user photos. Okay. Oh, one more example, badminton. And here, I was very impressed the computer labeled net, because if you look at this picture, the net, the badminton net is not that visible. So the computer has to reason, oh, I'm seeing a badminton game, I'm seeing athletes, there must be a net. So, okay, so that was one project we've done. So after doing that, we asked ourselves, can we apply that project somewhere? It's great to make computers to label these pictures. Can we actually start thinking about making smarter albums? So I'm sure, especially the parents sitting here, you probably have folders after folders of your kids, right? And sitting in your computer, because I'm a new parent, so every day I take pictures of my baby, and then my hard drive just blows up. And it's very annoying, actually, to organize these pictures. The only way so far I've been organizing it is using dates, so I say. But I imagine that one day I go back to China, show my friend. What if my friend says, I want to see all your baby's birthday parties? Or I want to see your child with his best friend, John. These are very common questions one day you and I would like to do with our pictures, but there's no such technology. So one day we would like that to happen. So there is an ongoing project in my lab. We just name it Smart Album Project. And one day we would like to make albums, break go into the contents of the pictures so that we can break the barriers of today's photo organizing programs and be able to do this kind of search. So it's also inspired by the fact that we have an explosion of pictures out there. So, Facebook, I was just at Facebook headquarters last week, and an engineer is telling me that they see 5,000 photographs uploaded every minute or so. And at YouTube, every minute YouTube sees 24 hours of videos uploaded. It's just a huge number, and you can imagine there's no way humans can handle the volume. So one day we have to make the smart computers to do that. So here's again a toy example that we are doing in our lab, making the very first try on how to organize photos in a smarter way than naming your folders by dates. So we have, here's a small experiment where we took 4,000 user photos, and we know these 4,000 user photos come from all kinds of events like wedding, birthday party, and so on. But we didn't tell the computers. We just show the computers 4,000 Flickr photos. And we tell the computers, can you organize it in smarter ways than just dates? And here's what the computer does. The computer, our program, was able to take advantage of what we did in the first project I showed you, know the what, where, and who, and then start organizing a hierarchy. Here's, for example, it organized all the event pictures and separated by wedding and birthday and under wedding, and further organized pictures of wedding gowns and flowers. For birthday party, it separated pictures of cakes and dance. Here's another example of football. It separated more detailed pictures of stadium shots or the match. Here's food. It separates sushi from cake and so on. So these are all automatically generated by our computer vision algorithm. And of course, this is a very small experimental try. We're still perfecting this, but this is one step closer in a smart way of accessing your digital library. Here's the overview of that 4,000 images and the organization. Okay, so that was 2 projects about telling everything we can in pictures. One of the most critical component in succeeding and building the best computer vision algorithm is about objects. Because objects dominate the visual world, and humans recognize many, many objects. So one of the projects that we have put a lot of effort in our lab with PhD students and postdocs is about recognizing many, many objects. So I'll give you a flavor of some of the work we are doing. So suppose you have a world of 100 objects. Okay, that's all. Your world only has 100 objects. And it's already a daunting task. When I was a PhD student, the best computer vision algorithm in the world recognized about 4 types of objects. And we have made tremendous progress since then. So here's a world of 100 objects, and I want you to recognize what this picture is about. So when the world is small, our old computer algorithm can do a search like this. It just look at the picture and try to search through its database and models and try to find the object that matches this. Here you go, it's a starfish. And what about a world of 1,000 objects? That's going to take at least 10 times the speed, right? What about today's internet world? Do you know, does anybody have a wild guess that how many objects, object categories like chairs, tables, a human adult recognizes in his or her life? What's your answer? 1 million. So this little girl said 1 million. Anybody else? You're in green. 1 billion. Wow, that's very optimistic. So the answer is we don't know. But we have a guess. So back in 1980s, before you were born, or at least the half of you were born, and before the internet existed, there was a psychologist in University of South California. He estimated using the biggest dictionary he can find in the world and everything, and estimated humans recognize about 30,000 object categories. Okay, and that number has since then been challenged, and actually, I don't know your name, but she said 1 million. We are estimating about 1 million. If you go to Wikipedia, the entries in Wikipedia are in order of millions. Not everything is visual, of course, but we think the order of magnitude is 1 million. But whatever that number is, it's posing a huge challenge to computer vision scientists, because we want to train computer vision algorithms that recognize tens of thousands and millions of object categories. And we want to make it very efficient. Otherwise, we have no hope of putting computers in the Mars or putting computers in your household. So our goal is to recognize many objects fast and accurate. So the hunch is that we cannot do that kind of search I just showed you one by one. To recognize this starfish, we want to just quickly get rid of so many irrelevant objects and keep cutting the space and quickly arrive at the right answer. Sitting behind this is pretty intricate math, and I'm not going to bore you today on a Saturday with equations. You have to still finish high school and possibly college to understand what the math is behind this. But I can tell you that my PhD student and I are having fun cranking through those equations. And here's a real result I'm showing you. Here is a world of 1,000 images, 1,000 object classes. And I show the computer an unknown picture here and say, hey, computer, tell us what this is. Our computer is able to do this very efficiently. It quickly, in the first iteration, it gets rid of half of the possibilities, and then quickly another half, and in just 4 or 5 iterations, we arrive at the correct answer. That's much better than scanning through the 1,000 possibilities. Here's another example. Okay, so our computer can tell us it's a Persian cat. Sometimes objects are so hard that no matter what you do, you wouldn't know what it is. Does anybody know the name of this object? Oh my goodness, so many hands. Let's get someone in the back. The boy in red. Yes. Very good. You said it's a mole. What did you say? It's a star. Whoa, let's clap. Give her a clap. That's amazing. Where did you see? Have you seen one?
Actually, I saw a picture of it.
You saw a picture of it? Oh, wow. Okay.
I went to summer nature camp and they were showing pictures of it.
Oh, the nature camp. Yes. Okay. It's next time I'll show you something harder. So it is. Yes, I think she's going to defy all computers. And yes, it's a star-nosed mole, but you said the right thing too. It's a mole. And when I saw this, I just said it's an animal. So I had no idea what it was. So, but sometimes we, in trying to build smart computers, before we know we're as smart as she is, before we know it's a star-nosed mole, it's also important to just be accurate no matter what. So now we're in the middle of building one of the, I'll show you the results in a minute, the biggest recognition system in the world, and we want to recognize 20,000 different objects and never make mistakes. And how do we achieve that, especially if we see some picture like this? Well, one way to do it is always know where to stop. So for example, she knows it's star-nosed mole. The boy over there says it's a mole. It's also correct. And I would just say it's an animal, and not wrong either. So this is our result. So we have an infallible classifier, that's what we call. The picture here is actually called, it's the object, the ground truth is called red fox, but the computer doesn't know what it is. Our algorithm, seeing this picture, has a hard...
I know what I actually know what that.
You also know that?
Saw a picture of a red.
Oh, wow. I'll show you something that I bet you don't know in one... just give me 1 minute. So the old style computer vision algorithm, we call it flat. Let's just forgive the jargon. It says it's a hyena, which is not totally correct. Whereas our algorithm, in a challenging case, would say it's a canine. So it always knows where to stop and never be wrong. And this is very important in many cases of application where we can make always correct guesses. So for example, the picture here in the middle, the third one and the second row, an old computer vision system would say it's airship, which is actually wrong. Here we really don't know what it is, at least we name it craft, which gives us some idea, and then we can refine our algorithm. So I want to challenge, what's your name? I have to know your name. Allison. I want to challenge Allison now. So, okay, let me just skip this. Allison, what is this? What? It's a car? Any other guess? It's a what car? Rocket car. So this is what a traditional algorithm would say, and I think it's wrong. Everybody would agree with me it's wrong. And this is what our algorithm says. We don't know exactly what it is, and we don't want to be wrong, so we call it a vehicle. Next time I'm going to call up Allison and ask. And Allison, what is this? Allison said it's a bird and crocodile. What would you say? It's a what? It's a mutant. Good answer. So, so this is what we say. It's an animal. So here's another example. So I don't know. Do you think it's edible, Allison? Allison says it's edible fruit. So I think it's an edible fruit. So so here are the of course. So the good news is that our normal world is not filled with all these things. So, you know, if we walk around the world with all these things, we have to really think about new algorithms. But this is just to demonstrate that, first, we're having fun in our research. Second, a deeper thing is that we're working hard in recognizing many, many objects, and in the case of really strange and difficult ones, we're also finding clever solutions that gets us a step closer, even though sometimes we don't know exactly what the answer is. So I'm very proud to report that at Stanford Vision Lab, we are the first one to have ever built a visual recognition algorithm that recognizes more than 20,000 object classes. Even Google doesn't have it. So, okay. So, so last, I'm just going to finish on a very small project that we're also very excited. The world is not just about pictures. We also are tremendously excited in looking at videos. Here is one research we've been doing in the lab with the PhD students in recognizing human movements. I really love these figure skating videos. That this is our human computer vision algorithm. You give them the videos, it recognizes what type of movements these athletes are making and is able to label the kind of spins that these kind of technical gestures that the athletes are performing. Here are the more complicated results. The top rows are 2 input sequences, and the bottom rows are 2 output sequences of computers. So we give the input sequence, and we have trained computer algorithms to actually take this, track the person, identify the person, and be able to label what the person is doing in real time. So that's another project we're doing in our lab. So, you know, I wish I had more time to sit here and tell you everything that's going on in our lab and also in the world of computer vision. But I'm going to stop here because I think it's more fun to take some questions. Oops. But we're doing exciting things. Computer vision is a very exciting field. And one day we would like to